This lesson's on the ideal gas law. Here are your objectives. Let's start by talking about the mole, which is a concept you might be familiar with from chemistry. 1 mole of any substance contains 6.02 times 10 to the 23 molecules of that substance, and we call this number Avogadro's number, capital N sub A. And 1 mole has the same mass in grams as the atomic mass listed on the periodic table. For example, 1 mole of helium, if you look on the periodic table, helium has an atomic mass of 4. 1 mole of helium has a mass of 4 grams. And this works out because 1 mole is actually defined in terms of the number of atoms in 12 grams of carbon-12. And therefore the rest of the periodic table matches up as well. You can think of a mole, 6.02 times 10 to the 23, as being like a dozen. It's always the same number of whatever we're talking about. And I've said molecules here, but it could be atoms, it could be any kind of particles. 1 mole is just that many of them. So we can ask, for example, how many carbon atoms are there in a diamond of mass 0.50 grams if it's entirely carbon, which, as we've said, has molar mass of 12 grams per mole. So we take 0.50 grams and we divide it by 12 grams per mole to find the number of moles. And that gives us 0.0416 repeat moles of carbon. And then we take that and we multiply it by the number of particles in 1 mole, 6.02 times 10 to the 23. In this case, we're talking about atoms. And we get approximately 2.5 times 10 to the 22 atoms. So that's how you would use it in calculations. And the formula that I'm implicitly using here is small n, the number of moles, is equal to big N, which is the number of particles, divided by capital N sub A, which is Avogadro's number. And this can be confusing because we're using an equation that just has a bunch of n's in it. Little n is the number of moles, capital N with no subscript is the number of particles, and capital N sub A is Avogadro's number. Now that we have that concept of the mole, we can use our previously discovered relationship between the pressure, volume, and absolute temperature of a gas, specifically that the product of the pressure and the volume is proportional to the absolute temperature, and now introduce the number of moles, the amount of gas. We do that by defining the constant R so that PV is equal to little n RT. In other words, R is equal to the product of the pressure times the volume divided by the number of moles multiplied by the absolute temperature. And R is called the gas constant, and it works out to being equal to 8.31 joules per mole Kelvin. Notice that what you're doing here is you are relating the amount of energy in a given number of moles of gas to the temperature, and we'll see that in more detail in a few minutes. We need to be careful about the units here, so let's take a look at the units that we will use for each of them. Temperature, as always, since we were working from our direct proportionality that we saw in the previous lesson, has to be in Kelvin. We've just said that the ideal gas constant is in joules per mole Kelvin, and N is just the number of moles. Let's look at pressure and volume, though. If we multiply these three together, we end up in joules. So the right side of our equation is in joules. That means the left side must be as well. Remember that 1 Pascal is a Newton per meter squared. So if pressure is in pascals, then volume must be in meters cubed. Multiply those two together and you get Newton meters, which is again joules. So we are going to use pascals for pressure and meters cubed for volume. Be careful that a meter cubed is a big volume. 1 liter, as you can see worked out here, is 1/1000th of a cubic meter. Or alternatively, 1,000 liters is equal to 1 meter cubed. So it's a big volume. Alternatively, we could work in kilopascals for pressure and liters for volume. And if you see, both of these are changed by a factor of 1,000 and in different directions. So their product will again be joules. So we could do that as well. Let's work through an example. We're asked to find the volume of 1 mole of any gas at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure. So we start from pressure times volume is equal to nRT, and volume therefore is equal to nRT over the pressure, and we need to make sure that we're working in the correct units. We leave moles as moles, and we use our gas constant, 8.31 joules per mole Kelvin, but we need to change our temperature to Kelvin. So 0 degrees Celsius is 273 Kelvin, And we need to change atmospheres to either kilopascals or pascals. Let's use kilopascals so we end up with an answer in liters. So 101.3 kilopascals is equal to 1 atmosphere, and when you work that out, you get approximately 22.4 liters. So that's going to be the volume of 1 mole of any gas at 0 degrees Celsius and 1 atmosphere of pressure. Let's shift now and talk about the average kinetic energy of a molecule in a gas. Using the ideal gas model, the ideal gas law, and Newton's laws, you can derive that the average translational kinetic energy of a single molecule of an ideal gas at an absolute temperature T is given by this equation. The average kinetic energy, or the average translational kinetic energy of that single molecule is equal to 3/2 the gas constant divided by Avogadro's number multiplied by the absolute temperature. We won't derive this, but starting from here, we can define a new constant equal to the gas constant divided by Avogadro's number, and that's called Boltzmann's constant, given this symbol. And working that out, because these are both constants, you get this number, 1.38 times 10 to the negative 23 joules per Kelvin. Again, notice that we're relating the energy of a gas to its temperature. So the equation now becomes this. The average kinetic energy of a molecule in an ideal gas is equal to 3/2 Boltzmann's constant times the absolute temperature. And we've been saying that the temperature is a measure of the average translational kinetic energy of the molecules in a gas, and this is the equation that makes that explicit and allows us to put numbers to it. Let's do an example. Find the internal energy of 2 moles of an ideal gas at 20 degrees Celsius. So first, note that we're being asked for the internal energy, not the average translational kinetic energy. So there's two things there. We don't want the energy of a single molecule, we want the total energy, and we don't just want the kinetic energy, we're asked for the total internal energy. But remember that if it's an ideal gas, there is no potential energy. So the internal energy is all kinetic energy. That's one thing we need to recognize. And if this is the equation that gives us the average translational kinetic energy for a single molecule, we need to multiply that by the number of molecules. In other words, if we start from the equation that we're given above, we are going to need to multiply both sides of the equation by capital N, the number of molecules. And we could do that and work out the number of molecules from 2 moles, but let's actually just do a little bit of rearrangement first. Let's put Boltzmann's constant back into the form that we saw before, and we'll actually get a new equation from this as well. So Boltzmann's constant was defined as being equal to the gas constant divided by Avogadro's number. Then we still have our temperature, and now we're multiplying by N on this side. And this on the left is what we're looking for. This is going to be our total energy, the number of particles multiplied by the average kinetic energy of each of them, and remember that average kinetic energy is the only energy that they have. The number of particles divided by Avogadro's number is just equal to the number of moles. So we can replace that, and we get 3/2 times little n, the number of moles, multiplied by the gas constant times the absolute temperature. So this is now a measure of the internal energy of this gas. And now we can just plug numbers in. 3/2 multiplied by 2 moles multiplied by our gas constant multiplied by our absolute temperature. And when we plug that into our calculator, we get approximately 7.3 kilojoules. So that shows you how you can derive now another equation from the ones given above, this one for the internal energy of an ideal gas. And to finish up, let's just notice that Boltzmann's constant gives us another way of expressing the ideal gas law. If we start from PV is equal to nRT, remember that Boltzmann's constant is defined as the gas constant divided by Avogadro's number. So we can rewrite this as PV is equal to R, therefore, is equal to Boltzmann's constant multiplied by Avogadro's number, rearranging this equation here, and then we still have the absolute temperature. Well, the number of moles multiplied by Avogadro's constant is just equal to the number of particles. The number of moles multiplied by Avogadro's constant is equal to the number of particles. I know it gets confusing when there's all of these n's. So the pressure times the volume then is just equal to the number of particles multiplied by Boltzmann's constant multiplied by the absolute temperature. The other version of the ideal gas law that we saw is in terms of the number of moles, and this one is now in terms of the number of particles. So that gives us sometimes an easier option depending on what's given in the question. So that's an introduction to the ideal gas law.